Sorry. Okay. Today we have a talk by Pedro Peixoto, and he is talking about analysis of grid imprinting on geodesical spherical icosahedral grids.
Thank you, Andreas, for pronouncing my surname correctly. It's not quite common. Okay. First of all, I have to thank a lot the organizers and the Institute for having me here. It's a really good opportunity. So, I'm a PhD student at the University of São Paulo in Brazil. I have to acknowledge my supervisor, Paulo. And what I'm going to present here is actually an attempt to answer a question that my supervisor made me in the beginning of my PhD. Okay, so I couldn't answer him at the time, and I think now I can answer him. Well, we'll see. Okay, so we're going to talk about grid imprinting. The way it goes, we'll have a short introduction with the motivation. I'm going to show some theoretical results, 2 theorems. Don't worry, I won't go into the detailed proofs of the mathematics. Then some numerical examples and some conclusions. So, to start with, we'll begin with an icosahedral grid. This is going to be like a play toy, but all the results are more general to any geodesical spherical grids. An important word here is geodesical. Okay. This only works for geodesical grids. So, as play toy, we'll have the icosahedral grid. We're thinking a quasi-uniform grid. I'll be using Voronoi cells here, but you can work with triangles as well. And I'm thinking of getting refinement due to bisection of the triangles. Okay, so you get several grid levels. So this is the kind of grid. Hopefully you are all used to this kind of thing, or have seen it somewhere. And as a play toy as well, I'll use a simple discretization, but I think it's quite common, which is the discretization of the divergence operator. And we'll think it, how do I point this? So we are assuming that the divergence of a vector field V on a point P0. We'll assume that this point P0 is somewhere in the beginning. We'll think it's a centroid of the cell, then we'll see what happens. And so this is the structure we have. In this example, it's an hexagon. And we are having 2 approximations here. So the first is to the divergence of the point is an average of the cell divergence. Then we apply divergence theorem, and then we use mean rule integration, midpoint integration, to get this formula, which is a usual formula for discretization of the divergence in a finite volume sense. Okay, so this is going to be our play toy.
Your Q's are midway between your P's?
Yes. Exactly, it's the midpoint. Okay, and so what was the question my supervisor asked me, and what motivated it was that I just popped this into Fortran code, and then I had a 40,000 grid points, and I just got a simple rotation field, so just zonal flow, and this is what I got. Okay, and that's what my supervisor looked and said, well, that's interesting because, well, it's grid imprinting. So what we see here is we are looking at the coarser grid showing up in a very fine grid. Okay, so the grid structure is popping up in the error of the divergence. And this is what we got curious. So what are so special about these cells than, well, nearby cells around here? So what is this cell in white has so different than this cell that is in red? Okay, was the main question that my supervisor asked me. And at the time, I didn't know how to answer, so I went to look. Well, first, before that, let me show, okay, this is, seems to be something strange, but what are the impacts that this can have in a, for example, a transport model? So here, just to show what happens with grid imprinting on a bit more sophisticated problem, I'm using the Lauritsen-Nair 2010 test 4, which is a non-divergence flow with background rotation, and just getting the transport of density. So this is the equation we're solving, and we are solving it in a semi-Lagrangian way, so that the arrival point will be obtained using the departure points, and it's assumed initial conditions, it's all equal 1. So the density function should stay 1 in all time steps, okay? But because of the discretization of the divergence on these 2 steps, we should get grid imprinting. And because we want to analyze grid imprinting, we will stick to a semi-analytic trajectory calculation so that we isolate the problem. So this is a third order Taylor expansion of the exact vector field. We are using cubic interpolation for scalars. We are assuming full velocities known at the edge, cell edge midpoints, and for example, a grid level 6. And it's very interesting what happens. Let me see if it will work here. Nope.
So you refine your grid by bisecting?
Yes.
So that's why it's a grid level
6. Yes, yes. That, in this case, this means that we have something like a...
It's uniform refinement.
Yeah, for now.
Everywhere. You're not
For
trying
now.
to do multi-resolution.
Yeah, for now. Let me just show you this movie, which I find quite interesting. Hope you do as well. Fine. Okay, there it is. I think there's a better one here. This one's better. Okay. So what happens is that, well, in the first time steps, grid imprinting occurred. I hope it loops around. Let's see. So you get grid imprinting on the first time steps, and what happens is that on each time steps, new grid imprinting is occurring, and it's also being transported. Okay? So in the end of a full cycle of the transport model, what we get is just a background noise due to grid imprinting. So this is what bothered us. So we want to treat in some way this grid imprinting effect. So this is the kind of thing that possibly in a shallow water model you will see a noise behind, and you won't see it directly as grid imprinting, but this is somehow what is generating it.
So you're only tracing the grid imprinting that comes from the beginning of the solution, I would expect?
No, it's creating new grid imprinting.
But shouldn't it create at the same place every time step?
More or less because of the transport. Okay, so it depends on your vector field, so it's transporting the grid imprinting as well.
But it looks like initially that non-divergence is quickly adjusted by the numerical method to...
Well, the picture is something like, this is not a good thing, but well, let's see. It just looks something like this. Okay. This is the pattern.
Number 5.
Yeah. So this is the pattern that unfortunately is not showing up so good in this movie. Okay.
You've unwrapped the gold. We've got it.
Sorry?
We should see all 5 here.
Yeah, but I'm seeing it here, but it's not able to see it there. I'm sorry.
Well, I think there's a wave number 5 underneath there, maybe, but the dominant wave number error is in wave number 2.
Okay, but this wave number 2 is because of the deformational test case. Because what it does is just like it's got 2 main spots, which it does like this. Okay, so you will see a wave number 2. That's a part of the test case. But what we should see in the grid imprinting here is a wave number 5, like a little spot here, 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 and here. Okay?
But it's smaller than the way number 2. Grid.
Yeah, it's smaller. Yeah, it is. But well, this is just actually to motivate. Well, it sufficiently motivates that it's something curious enough that should have some work done on it. So that's good. Okay. So the purpose of this was just to motivate, and the reason why this is our motivation because I'm working on my PhD on the development of a semi-Lagrangian transport method, okay, which I'll talk in the end of the talk. Okay, so let's start getting some answers. Okay, so this is the error, for example, in the rotational. This is the wave number 5 kind of thing. Why don't you get error here? Because the velocity field is small. Okay, and then let's look at the distortion, which I think is the first thing you guess would have correlation with the grid. And this is really curious because if you look at this point, you see that there are highly distorted cells around here. Well, the distortion I'm thinking is about length of the edges of the cells. So when a cell is regular, it has 0 distortion. When it has varying lengths of the edge sizes, then you get higher distortion. And then you see around the pentagons that you have highly distorted cells. And then when you look at the error, you have around here in white a cell that's got very small error. And just by this cell, you've got a cell with large error. So these two cells have high distortion, but they are having different results with regard to error. So a cell being distorted is not actually what is creating this pattern. Okay, this is the first thing you got to notice. Okay, this was somehow noticed in 2001 by Tomita and the Japanese group. And they suggested that the grid imprinted was related to regions of high gradients of area and distortion. The area pattern is really similar to this. Okay, so you get smaller areas around the pentagon. And okay, so this was, I mean, when my supervisor asked me why this happens, they said this happened because of this. And then that wasn't enough for me, that wasn't enough for him. We wanted a better answer. Okay, this is what I'm going to show you. Okay, so what are the two questions? The two questions are, what are the geometrical conditions behind grid imprinting? This is the first one. And what is the impact of grid imprinting on accuracy? These are the two main questions I want to answer I've gone too far, but I hope I can answer them in time. Okay, some theoretical results. So we are doing some simplifications here. So this is really a simplified thing, but I think it answers these questions well. So assume the velocity fields given at the midpoints of the edges of the polygon or precisely calculated. Okay? Then we have this discretization that I showed you. This first is an approximation of the average of the cell, and this one is due to the integration. Okay, what do we have? For a plane, this is quite easy to do. So the average approximation is second order if the point is a sinusoid. The divergence approximation is first order only in general. And why is this? We'll take a look at an example. Well, on a rectangle, this would be second order. If we have an odd number of edges, this may imply first order as a maximum, even if regular. So even if you have a regular pentagon or a regular triangle, you might be stuck with first order. And here is an example. Okay, you have here a regular triangle with the points P1, P2, P3, and the H here is the length of the three edges. Okay, and you get this simple vector field, which is just mainly in this x direction. And it's just a quadratic function. And the exact divergence is U1. And discretizes this. And the error is of order H. So you're stuck with first order.
So this is a theorem?
No, this is just a counterexample to show that if you have, even if you have regular polygon with odd number of edges, because it was something that I was discussing with Tomita when in the PDEs on the sphere, and then he came, well, but the pentagons are regular, so they should cancel out to have second order, and well, it doesn't. If you get exactly this example, but for a regular pentagon, you see that the error is first order. Okay.
Well, how do you define your discrete value?
Oh, it's just, well, it's on the centroid. In this case, it's...
You take the value on the centroid and for them...
Yes, yes,
Okay.
yes. It's just, I'm just analyzing a simplified case, which is this one. Okay, so the divergence at the point P0 is...
But you select your discrete value by evaluating the exact solution.
Yes, yes, yes.
But you can't change. You are not forced to do that.
Sorry?
You are not forced to do that.
Why?
You can select a better value.
You can select a better value than the value on the centroid.
But yeah, of course. If you know the analytical solution,
Okay.
you cannot tell me that the best value is to take the exact solution. You can approximate in another way.
Okay, maybe. Well, unfortunately, this is the way how it's implemented in general.
Yeah, okay.
Okay? So you just assume that the divergence on the point P0 is an expression of this formula. And what I'm stating here is that this would give you,
Of course.
yeah, first order approximation. Okay, but
But you
okay.
can imagine that you correct the centroid value in order to fix the problem.
Sure. But well, in this way that it's commonly used,
Yeah.
you will be stuck with this.
And there's some point at there where that is the exact divergence is given by
Exactly.
the.
Yeah. You have.
You can find a point.
Yeah. You could find a point. Well, curiously, the best candidate would be the centroid. You see, the centroid is the one that gives you a second order approximation for the average.
Yeah, that's true.
So it's
Yeah, that's true.
it's a good point to choose. Okay, but let's go. Otherwise, I won't have time enough to talk with. Well, let's see. So, what we came up with is a concept of alignment, which we defined as being. The concept is only defined for polygons with even number of edges, okay, because of the problem I've just shown, and we define it as being a cell which has edges 2 by 2 parallels and of the same size. So they not need to be regular, but they need to have a parallelism relation. Okay, this works for rectangles, regular hexagons, octagons, and we'll see that there are some weird things that can happen here. Okay, so this is our main tool. And what happens is for the plane, it's not difficult to show using Taylor expansions that if the polygon is aligned, and you need a condition that is the polygon is not degenerate. That means that the area is not too small related to the sides of the length of the edges. That you get second order approximation for that discretization. Okay, you need here P0 to be the center of mass. So. This was not difficult for a plane, but we want to use this on the sphere. So how do we extend these concepts to the sphere? How we define parallel edges on the sphere? I started thinking about several ways to do it, but the way we found was nicer to do this was defining a spherical aligned polygon using radial projection. So we'll say that a spherical polygon with an even number of edges is aligned if its radial projection onto the plane tangent to the sphere at its centroid is a planar aligned polygon. So we have a spherical polygon, we project it to the tangent plane on the centroid of the polygon, and look at this polygon. If it is aligned in the planar sense, then the spherical polygon is aligned. So this is the definition we came up with that works really nice. An important thing to notice that geodesics are straight lines in the projected plane. That's why all this is only for geodesical grids.
So this can be done only for a very small area, right?
Very small. Well, almost a full hemisphere. The polygon can be as big as a hemisphere. But in practice, you only use this for localized things. Well, so the theorem nicely extends using this concept to the sphere. Okay, although the proof is by no means trivial. Okay, so we have to project the vector field and the points to the tangent plane to do all the calculation, and this is quite a work. And well, the details, please ask me. I'm not going to show here, or wait for the JCP paper that will hopefully come out. It's under minor revisions at the moment. Okay. So this is nice in some sense, because if we suppose that we had the tangential components given at the midpoints of the edge all precisely calculated, the same results would apply for the curl operator. And the same thing for the Laplacian. If we suppose that the gradients were given at the edge midpoints or precisely calculated, then the same results would apply for the Laplacian. I know there are questions here, but there is an issue here with the classical Laplacian discretization.
So this says that on even number polygon it's second order, but can you also say that on odd number polygon?
Yeah, that's the counterexample I gave here. So if you have an odd number, what happens is that you can always get a vector field that will leave you stuck to first order. So if you have odd number,
it also holds for the curl operator also? Or
yes, also works for the curl operator. Yes, also works. Because it's basically the same. So for the divergence, we are assuming normal components and applying the divergence theorem. For the curl operator, we do mainly the same thing, but we have the tangential components. Okay, so.
Yes, and basically it's why some people want to use quadrilateral or some numerical method.
Exactly.
Not triangles.
But
consider that, for example, in finite element, it's quite easier to generate mesh with triangles.
Yes.
You can ask yourself why people still doesn't want to use quadrilateral for some application, and it's basically because when you are for a shell problem or viscoelastic calculation, you can have good element in quadrilateral and not in triangle.
I'll talk a bit about this in the end here.
This small.
I'll talk a bit about this in the end. I have a discussion part which I discuss what happens in these cases. Okay. So these are the theoretical results. So what's this got to do? Hopefully, I think it's got quite obvious. Well, the difference in the cell geometry results in difference in convergence orders of the discretization. So aligned cells have faster convergence than non-aligned cells, and that is why you get grid imprinting. And we'll see that numerically now. Well, to see this numerically, we need to define the concept, an index to represent this alignment. So we propose this one, which basically analyzes distance from the parallelism and the differences in the edge length of opposite edges. So it's just a way to measure what we said before. And this is the plot of the alignment index. If it's 0, the cells are perfectly aligned. The greater this alignment index, the more badly aligned it is, and this is the pattern we wanted. Okay. Now we found the geometric property that explains grid imprinting. This is the property we wanted. So it's alignment that it's implying on that structure. Okay. And okay, let's look at alignment versus distortion. So look at this cell. It's highly distorted. The edges have differences, but it's aligned, so you get good convergence on these cells. But if you look at a cell like this, it's roughly not too distorted, so the edge lengths are almost the same, but it's far from aligned, so you have problems on this cell. This is a curious thing. So distortion needs to be controlled if you want quasi-uniformity, but alignment is also important. So we have to look at these cancellation properties.
There are many metrics for distortion, right? I mean, distortion
is
another name for grid quality, right? And people want different types of grid quality, so they come up with different metrics for distortion.
Yeah, that's true. That's true. I'm just using the classical one, which represents how far away from a regular polygon it is. So, in the sense that how these length of the edges are far away from the mean edge length of the polygon. So you could say it would work the same if we get just the maximum edge length and divide by the minimum edge length. It would work the same with this one, which is the mean variation of the cell.
But typically, if folks are working with Ronite diagrams, they'll generate mesh quality by looking at the dual.
Yeah, this is the case.
And comparing it to an equilateral triangle.
And comparing it to an equilateral triangle.
Yeah.
Okay, but you will, well, the notion.
You check the triangle of dual mesh.
Right, and so that brings in not only grid length, but also angle.
Okay. That it's a point. I could bring it here. Well, I just analyzed it using what I found was most common was just analyzing the length of the edges. But this is just to see, well, you can have something that's, well, if you think in terms of angles, this would show up here. So you have high angles here and low angles here, and this cell is still aligned, but it's distorted in the sense of the angles. Okay? So it's a distorted cell, which has nice properties to work with. Okay? So let's go to an example. This is the vector field that appears in Heikes and Randall paper 1995. And we just do the arrow for the divergence. This is what shows up. This is the alignment index. You see a background error that is due to the actual vector field, but you see the grid imprinting and you see the alignment index capturing this grid imprinting really nicely. Okay? And convergence. Okay. So we separated. We assume that it's aligned if the index is smaller than 1%. And what we see in green is that the maximum error goes down by a factor of a second order. This is the order, this is the error. So you see it's a second order on the aligned cells. And on general, the maximum error is stuck with first order, as we've discussed already. That would happen. So, an interesting thing is, why is it convergent in the L2 norm, which is something that I've seen here in several talks. So, in the L2 norm, things have a higher order convergence than the other one. And it's curiously, if we look at, if we fix a cutoff point for the alignment index and look at how many aligned cells are in the grid, as we go into finer grids, the aligned cells tend to dominate. So the non-aligned cells are concentrated only around the coarser grid structure. So this is mainly why I think the L2 norm goes nicely into second order, but you lose it in the maximum norm. You lose the second order convergence. Okay. So we also looked at centroid over Voronoi optimizations. Unfortunately, it's good to see here, but it's not so good to see here. But the alignment index is capturing some structure of grid imprinting here, which also appears in the error. I don't know if you can see it. Is it possible to see here? More or less. Okay. Sorry about that. I can see it here. Okay. And well, the same convergence structure appears, and when you analyze the numbers, so we are stuck with first order on finer grids, and on the aligned cells we get second order. And this is the spring dynamics grid. Unfortunately, here you should be able to see these connections that we see here. Okay, so it's actually capturing what it should be capturing, and we get the same kind of convergence properties. Okay, so with this, well, we think that the cell alignment helps to explain, well, grid imprinting errors. We gave mathematical proofs for both the planet and the sphere, which is something rare. I realized that most things are done for the plane and assumed to work for the sphere, and so we try to work out for the sphere as well. The alignment index may be good for development and understanding of numerical methods on unstructured grids in general, and it could be a good tool for developing grids, and it can be extended to other operators. Okay, so now a question that has been asked me is, and which I also ask myself, is it possible to build a grid on a sphere with only aligned cells? I think this will be an interesting thing. So on a icosahedral grid, we are stuck because of the pentagons. Okay, although they are regular, they have an odd number of sides. On a cubed sphere, if we look at them, around the corners of the cube, the cells are badly aligned. Okay, this is something I didn't have a slide to show here, but it's something easy to see. If you just plot the cube sphere, you see that they're badly aligned there. So to get a fully aligned grid, you would need a grid with only cells that have an even number of sides. So we took a look with the octahedron grid generated, because it has 6 squares and the rest are all hexagons. But it turns out that because around these squares, the cells are really badly aligned. So it was, I think in the beginning we thought, oh, this might be a nice solution, but it didn't work out as well. We tried to do some iterative methods to improve the alignment, like some optimization procedures with the alignment index, and we got similar results to string dynamics and SCVT, so we just didn't carry on further. So if anyone has any idea, I'd be happy to hear. And just to finish, what could this have a practical use? This is what I'm working on. Well, we are making a hybrid method. Okay, so let's treat the badly aligned cells differently. Okay, so this is an example for a vector reconstruction. We're using Perot reconstruction, which is based on the divergence theorem. So curiously, with this vector reconstruction, we can make the same proofs of the theorems and show that in general they are only first order, but they are second order on the aligned cells. So what we did was, well, let's assume 95% of the cells are well aligned, and we are just using Perot, which is very cheap. Okay, and we just get the 5% most badly aligned cells, and we apply a higher order method, actually a least square reconstruction, which you need a larger stencil, and it's more costly. And what we get here is this blue line. This one is the maximum error of the Perot, and we get second order convergence in the maximum error, but we have a cost of a method that is 95% very cheap. So we are only spending computational money in the badly aligned cells. So in this sense, we separate the problem. Well, we use cheap method where the cheap method solves well, and we use a more expensive method where it's needed. We don't apply a more expensive method everywhere.
So previously you were showing us errors of the divergence operator, correct?
Yeah, this is just some preliminary thing.
Is this error of the divergence operator?
No, this is error of the vector reconstruction. Okay, this is I'm just showing a practical use of this and another example. Okay, this is just another example. I could have done a different discretization of the divergence to get it second order, a hybrid method. I could have done that, but I found it more interesting because I'm working with vector reconstruction. I found it more interesting to show this, that in some sense these results extend to other methods. So this alignment property may be interested in other methods. Okay, so this is nice. The green one is another method that I'm working on, and the red one is least square, full least square. So you see that with using least square in only 5% of the cells, we get almost the same results as using least square everywhere. So this is something nice. Okay. So what are we doing now? Okay, I'm trying to develop a hybrid semi-Lagrangian transport model with this kind of idea. And we are also asked by the reviewers of the paper to further on carry analysis to the usual Laplacian discretization advection operator and shallow water equations, and what happens on aligned cells, what is different from non-aligned cells, and this kind of thing. And thank you very much. This is how I feel about my PhD. So I'll be happy to take any questions.
Yeah. I mean, this is very similar to the problem with cube sphere grids, for example, where you have seams. I mean, it's not only the corners, but actually at the seams, you lose accuracy. Exactly. And so I guess what this suggests is that that there is actually seams along these sort of, I guess, and somehow but that says that there's a certain kind of smoothness in the interior.
Yes, exactly.
Those are seams.
Exactly. I would really like...
It's not surprising. I mean, somehow you have to distribute the pole singularity somewhere.
Yes.
The idea that it could somehow disappear is probably not reasonable.
Yeah.
But what we wanted to answer is, what are the geometrical conditions that that can give you, before you have the error, you actually know, well, it's going to happen here. Because this is clear on the cube sphere, this is clear on icosahedral grid, but when you apply optimizations, this may not be so clear. When you're on a locally refined grid, this is not so clear. I have already some results for refined spherical Voronoi tessellations, and it's nice to see that on the transition region, you get badly aligned cells and such things, and so you would expect these to be problematic. So
I think this alignment problem will remain, moving to the topology of the sphere.
Yeah. Well, it's a simple conjecture to say that maybe it's impossible to get a fully alignment, but we should be aware that it exists, and we should, well, at least be aware that it exists.
Yeah, like we are trying to divide a curved surface with some kind of a polygons. Polygons fit in a plane.
Yeah.
So when you map onto sphere, you'll have a problem.
You have a problem. Yeah.
Like other way could be to use circles instead of polygons.
Yeah. Okay. But that's a really different approach. Here, I'm just thinking about what
Pack everything with
geodesical grids, usual geodesical grids, and what happens in them, and trying to understand a bit better what happens.
So if I take that grid right there,
Yeah.
which are all equilateral triangles.
Perfect. Yeah.
Well, no, they're not perfect because they have 3 sides.
No. Okay.
Right? But if I combine them with a neighbor,
Yeah, they get aligned. I got some pictures as well. It's really nice to see. It's well known that on triangle C-grid methods, you get this low-high pattern that you get you get positive error and negative error. And we analyze a bit this on the paper, that what happens if these two triangles, you combine them together, they get a quadrilateral, and this quadrilateral is if it is aligned, then the error on one side will cancel to the error on the other side, and you would get a second order approximation on the quadrilateral, but you're getting first order on each one, so that's why you get this low-high thing. So it explains the pattern that happens on triangle C-grids in some way.
I have one more question.
Well, we discuss it a little bit better in paper to see. It's already been, this triangle thing has already been noted in some other works. So, but well, the alignment thing, when you gather together two triangles, is something neat that you see that's what's going on. Like one is underestimating and the other one is overestimating.
Like in all this analysis, when you go for a spherical triangle, the sum of the sides, the sum of the angles, like they will exceed the pi, right?
Yes, but this is all that is done here is for spherical polygons.
Spherical. So I mean, like there's Euler angle formula for the that is what is valid in the plane. There will be some kind of a deviation when you go for the spherical polygons, right?
Yes, you're right, and this is why it's not so simple to extend things for. This is why we have to build a methodology to extend things from the sphere to the plane to do all the work. Because if we want to work on the sphere, then we need to project everything to the plane to work on the plane. This is where it gets complicated. Any comments?
I mean, what's interesting inside
Questions?
it's not.
Okay, then let's thank Pedro again.